Hi, I'm Satnam, and I'm currently working at Acalvio Technologies as a principal data scientist. I have been in data science industry for more than a decade, and I have worked across multiple companies, including CA Technologies, Samsung, General Motors, and academically, I have a PhD from University of Connecticut, USA. And I look forward to tell you my stories from the data. So let me tell you a story about basic statistics. So when we take the basic course in a data science, you think about statistics, and that is your first thing, being taught in the course. And you learn about Gaussian distribution, Poisson distribution, and log normal distribution. And the question really comes to your mind is that, hey, why am I learning all this? Well, actually, it has all of that as real world applications. And let me give you one use case from the security industry. So there is an interesting use case in information security area, and we had to figure out what is the distribution of operating system in an enterprise network. And using the software defined networking, through some means we got the data, and the data had whole bunch of versions of operating systems. It has Windows, Mac, and Linux. So the first thing comes in a mind is that this, what kind of distribution is that? And that's pretty much a categorical distribution. And we take that distribution and use that for deploying our sensors. And sensors also take the sampling from that distribution. So this is a very interesting use case where we are employing statistics to really embed the concept of sampling with the statistics and along with the security, information security area. So let me move on to the next concept. And the next concept I want to talk about is like when you get a lot more data into the enterprise, how do you update that? So this is really something like in an enterprise, some users may be added on and they will be also leaving, or so the devices in an enterprise are not really constant. So it will be changing. So the distribution of operating systems and the various devices would be changing as well. So in that case, how do we update our distribution? And that's where the Bayes rule and the Bayesian framework comes into the picture. So what you do is that you assume certain prior distribution, and that prior distribution was something I was alluding earlier. It was a categorical distribution. And now you get some update, and that update you model it as a Dirichlet distribution. And when you do a Bayesian update of that, so you take the likelihood and you take the prior and you use a Bayes rule, then you get posterior distribution, and it is again a Dirichlet distribution. And then you can use the Dirichlet distribution to get the distribution after the update. So let me briefly describe this information security area. So right now in our enterprises, what we do is we secure primarily at the perimeter. We have firewalls, we have intrusion detection system, intrusion prevention system, and all these systems actually do the perimeter control, and they don't let the malware or hackers or adversary attackers to get into the system. But recently, in last couple of years, what has happened is the attacker side has become more advanced, and they are able to do a lot more attacks very easily through social engineering and through phishing attack. And the defense side is not able to prevent those, because once they are into the system, they can do whatever they want pretty much, because they get the authentication and they get the higher privileged passwords, and they keep on moving through their target to stealing the data and as well as stealing the IP and the source code. So this is a very prominent problem in the industry. You may have heard of Sony attack and what happened at Target. All these are various examples of cyber attacks and information security attack. And this is the big problem in information security area. So as I was alluding earlier, that we are using statistics to come up with what is the distribution of the machines in an enterprise. And then we take the sampling distribution of our deception sensors also with the same. And the intent is that we want to blend our technology within the same enterprise and having the similar distribution. And in this way, actually it makes one of the key features of our product. And this actually is one of the key ingredients of our product. So let me tell you another story about EDA, exploratory data analysis. Well, the first thing a data scientist do is actually look at the data and get a feeling of it. And what I mean by that is do a various kind of plots. And those plots may be as simple as a bar chart, or maybe as simple as a bubble chart or a stack diagram or anything. The intent is to get some feeling of it, what are the various attributes, and how many missing values are there, and how it is actually going to help to solve the business case, what you are trying to do. So let me give you one example. And this is an example from my automobile experience. And in that example, I'm showing it here at the visualization here. You can imagine that we have a whole bunch of data. The data could be coming from dealers, could be coming from telematics, could be coming from actual automobile itself. And we actually fuse that data, we correlate that data, and that get many insights. So one of the questions which comes out is, if you're looking at the claims, warranty claims, and the obvious question is that what are the top 10 or top 20 warranty claims that an enterprise or any OEM has to address? So you would like to look at that more with the time and also with the various models. Could be Chevy Impala, or could be Spark, or could be Avio, or could be any vehicle to say. And you would like to analyze that. And it can be the first shot can be looked at as a bubble diagram. And what you see here is, in the x-axis you see the model year, and in the y-axis you see the number of claims, and the bubbles here represents the size of it, and then also they represent the different colors represents the different models. So it visually comes out very naturally. The another use case of EDA, I would say, is giving some kind of wow factor to the user. Because eventually the machine learning or the data science algorithm is going to be at the back end. And whatever is going to come is actually going to be at the front end. So what do I mean by that is, so let's take another example of my current organization at Acalvio. We are making a very new generation of UI where we are taking a state-of-the-art technology stack to give very interesting visualizations which may cover lots of animation, and it can cover the aspects of big data visualization as well. And then we empower the visualization and the machine learning and the data science together. We weave in both the concepts together. So when we talk about the big data visualization, think about it. If you have in an enterprise, you have hundreds of thousands of machines, how do you visualize that? So these kind of questions actually extend the concept of visualization to another extreme altogether. So the traditional dashboarding techniques may not work. So there you need to go and use something like a D3 or something more the latest state-of-the-art technology where you can visualize multi-objects in a multi-dimensional way so that you can look at the big data. So let me give you another example of technologies which is into the space of unsupervised machine learning. And this is very important because lots of data does not have labels. And that's where the another big bucket of technology falls into, and that technology stack is called anomaly detection. Now, what are the different places where we see these kind of techniques being applied? Let me start with fraud detection. So all the credit card industry you see, we want to detect the frauds over there, and those frauds are very less, but obviously they don't have labels, right? And they are embedded into a whole bunch of benign transactions, the benign credit card transactions. And so the credit card companies need to figure out where the frauds are happening. You take another example from, say, industrial equipments. So we have wind turbines, you have nuclear plants, or automobiles and aerospace. They have complex systems, and hundreds of thousands of sensors are there, components are there, and with these components, they have to work and function the way they are supposed to, right? Now, whenever some kind of a fault happened over there, how do you detect these faults? This is, again, anomaly detection application. Let's take another example of, say, information security area and also information infrastructure area. When you go to a big enterprise, they have hundreds of servers and they need to monitor thousands of processes. How do you monitor them? You can't put analysts on each of the process or each of the server. You need to have some kind of automated tool that will be monitoring that data, and then it will be flagging any kind of anomalies which are getting triggered so that system admin can go and fix those issues. So these are the various places I described where anomaly detection plays a big role. So next I will get into more of how these anomaly detection problems are being solved in the industry. There are anomaly detection techniques are not just from one place. They are actually into multiple buckets. The first one, let's say we talk about statistics. So you can actually take the data and say that, hey, it follows certain kind of distribution. And then what you do is you say that, hey, I have a distribution of nominal or the baseline. And then you say that, hey, if I have a deviation from the baseline, then I will call it as anomaly, or I will call it as an outlier. Now, what has been traditional way of doing it? You use a Six Sigma approach, or you say that, hey, I have a Gaussian distribution, and if I have something on 3 sigma here, 3 sigma here, and then all the points, those are not in that bucket, that makes outlier, and those are anomalies. That's been there for a long time, and you won't be surprised, many of the products are still using that technology and still using that heuristic. To some extent it works, but my take on that is it triggers lots of false alarms and lots of misdetections, and I think nobody has time to look at it. In a typical example, I would say is in information security area, there could be alarms and alerts which could be into some few hundreds. Okay, and then you expect an analyst to look at all of them. I mean, it would take probably weeks to look at that, but he has just a day to solve those few hundred alerts. So he's just going to pick up few of them. So we need to have advanced technologies that can solve anomaly detection problems. So let's say we start with more like machine learning based approach. In the machine learning approach, what we could do is, instead of taking some kind of assumption on the distribution or Three Sigma approach, we can take a clustering approach. We say that, what are my clusters for baseline? And then the points, those are away from the cluster, those are actually anomalies. So this is an interesting way to look at. And I'll tell you, in our infrastructure monitoring system, we apply DB scan algorithm, which is a more of a density-based clustering algorithm. And that works pretty good. And in fact, I have seen examples from Netflix. They have been using DB scan algorithm, and they have reported that they are getting excellent results from DB scan. Another algorithm which works pretty good is kernel density estimator. So you apply kernel density estimator, and then you model it, and you fit the model, and the points, those are away from that fitted model, are sort of your anomalies. Another trick I would say is, don't apply at the whole data. So in a sense, like obviously you are doing the partitioning of the data, training and testing and so on. But what I meant by that, if your data is time series data, you need to actually look at more of a sliding window approach. So what you do is you take one sliding window, you train on that, and then you apply on the next window. And that trick works very well with the time series data. So let me give you another example of anomaly detection. And this one is my work at UConn. And we were working with DARPA on one of the project was actually figuring out so-called terrorists or the bad elements out of a population. And the problem set was like we have a whole bunch of synthetic data. It was not a real data, it was more of a synthetic data. And the data actually included the interaction among various entities, various people, obviously, the interactions of money transactions, or maybe, their discussions or the talking, and then also their travel transactions. And now think about it like, if you need to apply this kind of a model at an airport and you want to do screening, obviously profiling is highly used to figure out, whom you should screen and not screen, right? And that's where the anomaly detection also come into a picture, that you need to really figure out what are those anomalies and what are the entities or people whom would you like to screen and you would like to go and do further surveillance. So I know that this topic is very much sensitive, but from machine learning and data science point of view, this is a big challenging problem, and this has been an area of research for quite some time. Why this is so challenging is because there is a lots of noise and the signal is very less. So you want to go and figure out the signal, and the noise is too much, so signal to noise ratio is pretty low. And in other words, you can say that this is a problem of so-called unbalanced data set, right? I mean, you really don't have any labels, and also you have a whole bunch of data which is sort of, you are calling it as your baseline or the nominal behavior. and then you want to flag anomalies out of it. So I gave you another example where we can apply anomaly detection. And one thing I would like to add on is we may not be straightforward able to apply the existing set of algorithms. You may need to tweak it, and you may need to modify it based on the problem you are solving. And then you need to enhance it. So remember, we were talking about anomaly detection, and just the next step to that is actually talking about unbalanced data set. And when I described anomaly detection, it was one of the framework to solve that problem. Now, if you have some labels available to you, right, like in the credit card fraud example, you know that, hey, these are the frauds, those are happened. And you do have a label that these are the frauds, and these are the transactions which are not fraud, right? Those are benign. So can I use something else? Can I apply some more techniques to really solve my business problem of detecting the frauds? Well, obviously, yes, you can. And the way to handle this kind of unbalanced data set is, first of all, can you work on the sampling techniques? Can you sample more or less? So what do I mean by that is you sample more from the class which has less data. So like fraud. Fraud has less data, so you sample more from there. And also there are very interesting formulations and interesting ways of sampling as well. You just don't take the data and then copy it. You can actually look at the various attributes of that particular transaction, and then you can randomly change that. And that could give you different data as well. And then how much to change, or how much deviation it should make from the benign. You can bring all those aspects into the data. Another aspect I was saying, that undersampling. Like you are applying oversampling for one class which is fraud, but another class which is your class 0, which is not fraud, what you do is you do undersample. So you actually take less data from that particular class, and you take more data from your fraud. Now you constitute your data set and then start training your classifiers. Now I can train my classifiers something like naive Bayes or a random forest or SVM, and then I can obtain the classification accuracies. Another trick which I will give you is use combination of classifiers. Don't use just a one, use whole bunch of them. And then you can also use an ensemble of that. And that will give you higher accuracies as well. One more thing which I do is I tend to keep some kind of a lower bound and also upper bound as well. So in a case, lower bound means like I know that naive Bayes would give me a lower bound. And then if I go to the upper bound, means like I'm kind of applying a deep learning kind of thing. In that case, I would get sort of an upper bound, but there is sort of a risk that you may be doing overtraining on your data. So if you are coming up with your own algorithm, you can actually go and see, hey, where I am in this spectrum. So I talked about sampling, I talked about the classification algorithms. So the third aspect I want to talk about is how do we evaluate these classifiers? We can't use classification accuracy because your data is highly unbalanced. So in this case, what should we do? We can use some metrics like precision, recall, or F score and F1 score. And these metrics will actually give you a lot more insights on how your classifiers are working on this particular data set. So let me talk about more of a hypothesis testing and how I have used in my experience. So I'll give you a very interesting application, the way it actually happened in my work. So we were working on a very interesting use case in smartphone industry, and what we were doing, we were collecting a whole bunch of data for the user and in your smartphone, and we were doing some kind of machine learning and data mining on the phone. And our intention was that to enrich user experience by giving more data mining and machine learning churning, and then giving it better experience for the user. So what do I mean by that? Like give a better contacts, give a better gallery, or give better calendar by munching all different data streams for that user from various data sources. So whatever user is doing on that phone, the phone calls he's making, or the SMS, or social network data, all this kind of a data, we were fusing it and then giving the better experience. So in that, what actually happened was, like, we came up with an algorithm and we applied it and all was working good, but then the question really came, hey, is that going to be scalable? Is that going to be working for all kinds of people? Because if you can test only with few hundred people, right, how can you be sure that it is going to work for millions of people, and in that setting which is more of a data related? So what we said is, can we actually do some kind of a hypothesis testing? And we say that, hey, do I have enough confidence that it's going to work or not work? So in our use case, it was like, if I have multiple names, like something like Satnam Singh PhD, or Sat Singh, is this the same person or not? Now, if I need to say this person is same or not, we came up with an algorithm which was more based on text mining and so on. And then we tested it on some 20-40 users, and then we said, hey, algorithm works good. But now the question comes, is this algorithm going to work for all kind of people? Is it going to work on Korean names, or is it going to work on Russian names, or is it going to work on American names? How would you test and how would you validate this kind of algorithm? So obviously you can't go and figure out this for the entire population. So this is also pretty much like when you do your survey, right? Before the poll happens, and the polling is done, sort of like the surveys are done, and the survey results sometimes mess up, but sometimes they do a good prediction, right? So all this is pretty much falls into the hypothesis testing problem, and also into the sampling techniques. How do you sample? So one of the way actually we use it more as Monte Carlo simulations. So what we say is that you have some data which is coming from a distribution, and you sample it multiple times by keeping the original data with replacement, and then you sample it more and do it multiple times, and then compute the statistics and look at the distribution of that statistics, and that will give you an indication that, hey, is it going to be the result what you are looking at or not? So what we do is something called Monte Carlo simulations. In the Monte Carlo simulation, we have a population. In that population, we randomly pick up some samples, and then we constitute another subpopulation, and you compute some statistics of that, like something like mean, standard deviation, skewness, kurtosis, and so on, right? Now that is your one subpopulation. Now what you do is you again sample it more, and then you again constitute another subpopulation. And then you again pick it up and then do your third subpopulation. And you do it like some thousands of times. Then this will give you another distribution of mean, skewness, and kurtosis, and so on, right? Now, on that distribution, you can actually look at how's your mean and the variances behave varying. And if you look at that distribution, that will give you very much confidence, and you can look at that and say that, hey, is this the value what I'm looking for? And this is the value for my accuracy of my algorithm. And that can give you some sort of a statistical framework to go and claim that, hey, this is what my algorithm going to give you if there is a randomness and if there is a variability in the data. Let's talk about clustering. Clustering is a wonderful set of algorithms which you can apply it for unsupervised machine learning. So let's say you have a data in which you don't have labels. Now what you do? You actually apply clustering. And multiple techniques are available for doing clustering, something like k-means or hierarchical clustering or db-scan algorithm, and many such techniques are available. Let me give you an interesting example where we applied clustering and we actually made it as a part of our product. And it is from my automobile experience. And data was something like in an automobile, there are a whole bunch of sensors. And whenever there is a fault, these sensors raise some kind of an error code. And these error codes are getting recorded in the ECU, electronic control unit. Now, when you are examining all this data, which are coming from engine, something like engine speed, vehicle speed, engine control module voltage, also something like the time as well, what time it happened, how many ignition cycles, and many such things. When you look at all this data along with the error code, you would like to figure out the root cause. When these faults are happening and why are they happening? And what is the root cause behind it? So in this setting, we applied clustering. And we were looking at, first of all, we were looking at these parameters. And we were doing the clustering for each of these parameters individually. So something like you are looking at engine speed and you are doing a clustering of the engine speed data and then seeing that when the fault happened, were there a major cluster? Was it happening when the car was starting? Was it happening when the car was at a steady state? Or when there was too much of variation in the speed? What were the conditions on which the fault actually happened? And you can also look at the pairs of parameters, something like engine control module voltage and vehicle speed, and then look at the clusters. And these clusters will give you insights that when these faults are getting triggered, under what circumstances and what operating conditions those faults are getting triggered. And this was very useful, and this gave a lot of insights to our diagnostic engineers, and they could actually take that insight and go back and apply it in their algorithms, in their diagnostic algorithms. So I gave you an example of clustering in this automobile DTC so-called error data and also the operating parameter data. Let me give you another example where we can also apply a k-means algorithm. So we get a whole bunch of data from smartphones, right? And we want to look at where, in which kind of locality I should sell what kind of a smartphone, right? So if the smartphone manufacturer want to do some kind of a marketing campaign, he can actually use clustering, and they are pretty much using it to do the customer segmentation, to figure out what kind of customer audience to target. And they do clustering and figure out how big are these clusters, what are the characteristics of those clusters, and what is the profile of the consumers in those clusters. And then they target different marketing campaign or different scheme to really launch the product and also make a better sale of their product. Let me get into the linear regression. So linear regression, you have read in your classes, is one of the fundamental technique when you want to do prediction and you want to apply it on a continuous data. And we use that obviously as our first technique to apply it. So my take on a linear regression is like whenever you want to apply something like a first and for classification, for prediction, you can just use a linear regression as your lower bound. And you apply that and get the insight which you can use it to get to design your own algorithm or choose the one which will give you the better results. So if you take an example of that automobile, we want to, let's say, predict how many faults going to happen in the time, in future. So we can take the data, what is happening right now in the historically and the number of faults, and then we can predict the number of faults in future. And linear regression is a classical example for that. You can use linear regression and fit the model. And obviously, you have to be careful what attributes you are using to model your linear regression. And that gives you an example of linear regression.